Hello everyone, today I will process my homework for PLC book. In this project, I use paper PLC control uh, pneumatic piston. The control logic is implement in three programming language: LD, FBD, and ST. The PLC program is downloaded into real hardware. The FluidSi is used to demonstrate the pneumatic principle. The objective of this project is to control a piston using PLC. First, I use timer specifically tone to create a delay function. Second, I use a center I use a counter CTU to count the number of working cycles. Third, I implement the same logic in three programming languages. Finally, FluidSi is used to solve the pneumatic working principle. This slide shows the system status. There are two independent parts in this project. Part A is PLC hardware control. The start button sends a signal to back for PLC. The PLC output signals to control the selenium volume valve, which drives the real cylinder. Plan B is a function FluidSi simulation. FluidSi is used only to simulate the pneumatic circuit. It's not directly connected to the PLC program. Now I will explain the control logic. When the start button is preset, the cylinder moves forwards. When it reaches limit switch S1, the timer starts in a 3-second delay. After 3 seconds, the cylinder moves backward. When it reaches S0, the counter increases by 1. When the counter resets the preset volume, the system stops automatically. This creates an automatic reciprocation motion. This is the flowchart of the system. The process starts from the start button. Then the cylinder moves forward after reaching the limit switch. The timer is activated. Then it moves backward. After returning to the initial position, The counter increases is if the counter research the preset volume, the system stop. This side shows the PLC hardware step. I use a buffer PLC. Input include the start button, 0 S0 and S1. Output include Y1 for forward motion, and the Y2 for backward motion. The PLC runs in a scan circle. It reads inputs, executes logic, and update output continuously. This is the leader degree programmer. LD is simulator, similar to traditional relay control skills. In this program, I use a self-holding skill for the start button. Atom timer for delay, and a CTU counter to control cycle. LD symbol and widely used in industrial automation. This site shows the function block diagram. FBD use block to represent logical functions such as timer and counter. The connection between block clearly show the data node. It's very suitable for modular and status programming. This is the status text program. ST is similar to high-level programming language like C. It uses if statements and logical conditions to control outputs. ST is powerful and flexible, especially for complex algorithm. I use term, which means timer on delay. In this input signal, PT is the process time. Q becomes true after the process time has implements. The timer ensures the piston stays for 5 seconds. I use CTU, which means count up. CU is count trigger signal. PV is process volume. CV is current count volume. When CV research PV, the system stop. This side shows the function simulation. This side shows the FluidSi simulation. It includes a double acting cylinder. Also a solenoid volume. Let limit switch, and an air support system. PLC help visualize how the uh, pneumatic system works. This design saw a 12 PLC program running on hardware. The program was downloaded into the buffer PLC using the programming software. After downloading, the PLC execute the control logic in real time. As we can see on the screen, the leader diagrams is running, and the logical status change is dynamically according to the input signals. When the start button is pressed, the PLC activate the forward output. After the timer delay, the backward output is active. The demonstrate that the system is not only simulation, but it's open renting and on real instruction is industrial hardware. In conclude, three programming languages implement the same logic. The PLC program runs real hardware, but the same verifies the numerical principle. Timer and counter are very common in instruction automation. This project improves my understanding of PLC execution control. And thank you for listening my homework. See you next time.